To have valid results output for any parametric test statistic, the associated parametric assumptions must not be violated. They must be satisfied by your dataset, and you must ensure your data is tenable for the analysis. Otherwise, the results you will get may not be valid. This video is born out of popular demand from many viewers who have seen my video on binary logistic regression analysis in SPSS, and they have requested to know how to test for the assumptions. If you have not seen that video on binary logistic regression analysis in SPSS, then you can type this link on the browser to see the video, or click on the same link given in the description section of this video. So, in today's video, I'll be demonstrating how to perform the test of assumptions for binary logistic regression analysis in SPSS, and I'll be using the same data that I used in the binary logistic regression analysis video. But before I go into the demonstration, let me quickly reintroduce the parametric assumptions to you. To perform binary logistic regression analysis, the following assumptions must not be violated by your dataset. 1. Your dependent variable should be categorical and measured on a dichotomous scale. That is, it should have mutually exclusive and exhaustive categories. 2. There should be one or more independent variables, which can be either continuous or categorical. The continuous variable should be measured on interval or ratio scale, while the categorical variable could be ordinal or nominal variable. 3. Your data should have independence of observations. That means the observations should be independent of each other and must not be repeated or paired. 4. If your independent variable contains continuous variables, there should be a linear relationship between the continuous variables and the log odds or logit transformation of the dependent variable. 5. There should be no multicollinearity among your independent variables. This means there should be no two predictors or independent variables that are too highly correlated. So multicollinearity can be a huge problem to the logistic regression model. And 6, there should be no significant outliers in your dataset. Presence of outliers in your dataset can make your model produce invalid result outputs. So there must be no outliers. The question now is, how do we test for these assumptions in SPSS? Or how do you test whether your data is tenable for binary logistic regression analysis? However, it is not all the assumptions that will require a test statistic procedure, but I will take the assumptions one by one and perform the required test statistics only where necessary. Without further ado, let's get into the demonstrations. Assumption number 1. The assumption number 1 states that your dependent variable should be categorical and measured on a dichotomous scale. To be categorical means it should be a nominal variable, and to be measured on a dichotomous scale means the category should be 2, mutually exclusive and exhaustive. Now, click on the variable view button to go to the variable view window and check the dependent variable hypertension to see if this assumption is violated. As you can see in the measure column, the dependent variable hypertension is a nominal measure. Now click the value label to open the dialog box. As you can see here, the category of the dependent variable is just 2. That is 0 for no and 1 for yes. This means that the dependent variable hypertension is categorical and dichotomous because it is mutually exclusive and exhaustive. This means that the assumption number 1 is not violated. Now let's proceed to test for assumption number 2. Assumption number 2. The assumption number 2 states that there should be one or more independent variables which can either be continuous or categorical. The continuous variable should be measured on interval or ratio scale, while the categorical variable could be ordinal or nominal variable. As you can see from these variable properties, the independent variables are gender, age, and blood pressure. The gender is a nominal variable, which is categorical, while the age and blood pressure are scale variables respectively, and they are continuous variables. This means that the assumption number 2 is not violated. Now let's test for assumption number 3. The assumption number 3 states that your data should have independence of observations. Now let's proceed to the data view window. As you can see from this dataset, each observation is independent of each other because no one case is matched or paired as each row is not repeated. Each row is an individual case and represents an observation. This shows that the data has independence of observations. However, this method of verifying this assumption is not statistically sufficient. So since independence of observation has to do with autocorrelation, I will use a specific test statistics that is called W-waxing to test whether the independent variables have independent observations. Now go to the menu bar and click on Analyze. From the submenu, put your cursor on Regression, and from the drop-down options, click on Linear to open the Linear Regression dialog box. Here, we will pretend we are performing a regression analysis. In this dialog box, your data variables are in the box on the left. From here, move your dependent variable to the dependent box on the right. So, I will click on hypertensive patients and then click on this transfer arrow key to move it to the dependent box on the right. Thereafter, transfer your independent variables to the independent box on the right. So, I will click on gender, hold down the shift key on my keyboard, and then click on the blood pressure to select all three of my independent variables. Then click on this transfer arrow key to transfer them to the independent box. Now, click on the Statistics button to open the Linear Regression Statistics dialog box. In this dialog box, uncheck the Estimates and the Model Fit. Then check the box for W-waxing. This selection will calculate the W-waxing statistical value and produce the result in the model summary table in the output window. Then click Continue to close this dialog box. Now click OK to perform the calculation and produce the model results. As you can see, the regression results have been produced. So kindly proceed to the model summary table. In this table, locate the W-waxing column. And as you can see, the statistical value of W-waxing is 1.969. However, the acceptable range of W-waxing is between 1.50 and 2.50. This means that W-waxing's value less than 1.50 or greater than 2.50 indicates that the error terms of a regression model are not independent. So for your data to have independence of observations, the calculated W-waxing value must be within the range of 1.50 to 2.50, or approximately between 2 and 3. So as you can see from this table, the W-waxing value is 1.969, which falls within the acceptable range of 1.50 to 2.50. This indicates that the data has independence of observations, and as a result, the assumption number 3 is not violated. Now, let's proceed to confirm the assumption number 4. The assumption number 4 states that there should be a linear relationship between the continuous variables and the log odds or logic transformation of the dependent variable. To carry out this test of assumption, we have to create new log variables for the two independent continuous variables, which are age and blood pressure, and then include them in the logistic regression analysis as interaction variables. Now, you may want to ask, how? Let me show it to you. Go to the menu bar and click on Transform. From the submenu, click on Compute Variable to open the Compute Variable dialog box. In this dialog box, we want to calculate the log of age of patients and the log of blood pressure respectively. Now, let's start with age. Go to the Target Variable box and enter a new name for the age of patients. Let's call it lineage or ln_age. Thereafter, go to the Functions Group box and click on All. Then in the Functions and Special Variables box, locate lin or ln, which is called lin function for log. When you have found it, click on it, and immediately the synopsis of the function is highlighted in the box on the left. Then click on this transfer arrow key to transfer the function to the numeric expression box. As you can see, the function comes with a question mark inside the parentheses. The question mark is asking you to provide the variable whose log you want to calculate. So go to the box on the left and click on the age of patients. Then click on this transfer arrow key to make it replace the question mark as you can see. Then click OK to produce the log of age as a new variable added to the dataset. Now, I will quickly repeat the same procedure for the second continuous variable, which is the blood pressure of patients. Now, let's leave the output window and go to the data view window. As you can see here, the two newly added variables are log of age and log of blood pressure designated as ln_age and ln_bp respectively. Now let's go and check if there is a linear relationship between the continuous variables and their log-alls or logistic transformations. Go to the menu bar and click Analyze. From the submenu, put your cursor on Regression, and from the drop-down options, click on Binary Logistics to open the Logistic Regression dialog box. Here, you will pretend you are performing a binary logistic regression analysis. In this dialog box, you have all the variables in your dataset in the box on the left. Now, I will click on hypertensive patients as my dependent variable and move it to the dependent box at the top right. Again, I will click on the gender, age of patients, and the blood pressure of patients as my independent variables and transfer them to the block 1 of one box at the bottom right. But remember that we are not performing a binary logistic regression analysis. We are just using the procedure to help us test for one of the assumptions. Now, because we are interested in knowing whether there is a relationship between the independent continuous variables and their log-alls or logic transformations, then you will have to include the continuous variables and their log-alls to the independent variables list in the block 1 of one box as interaction variables. What do I mean? Let me show it to you. Click on Age of Patients, hold down the Control key on your keyboard, and then click on the log of age to highlight the two variables at once. Immediately the two variables are highlighted, this interaction transfer button is activated. Then click on it to transfer the highlighted variables as interaction variable of age and log of age. Repeat this process for the blood pressure of patients. After you have completed the process, go straight and click OK to produce the model outputs. As you can see, the model results have been produced. Scroll down to the table of variables in the equation. In this table, concentrate only on the rows of the interaction variables and consider only the information in the p-value column designated as xig. If the p-value of the interaction term is greater than 0.05, then there is a linear relationship between the continuous variable and the log-alls. But if the p-value of the interaction term is less than 0.05, then there is no linear relationship between the continuous variable and the log-alls. But as you can see from this table, the p-value of the interaction between age and the log-alls is 0.419, and the p-value of the interaction between blood pressure and the log-alls is 0.102. This means that the p-values in both interaction cases are greater than 0.05, and this indicates that there is a linear relationship between the continuous variables in the independent variable list and the log-alls or logic transformation of the dependent variable. So the assumption number 4 is not violated. Now let's proceed to test the dataset for assumption number 5, which is the issue of multicollinearity. Assumption number 5 states that there should be no multicollinearity among your independent variables. For this assumption, there are 4 ways to check for multicollinearity in your dataset. They are 1. Tolerance. 2. Variance inflation factor VIF. 3. Condition index. And 4. Bivariate correlation method. For your interest, I will refer you to see my video on test of multicollinearity of data in SPSS. In that video, I had given detailed description and demonstration on how to test for multicollinearity using the 4 methods listed above. The link to the video is given in the description section of this video. But in this video, I will just demonstrate how to use bivariate correlation method to test for multicollinearity, while you check out for the other methods in my previous video. Now, let's do it. Go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Correlate. And from the drop-down options, click on Bivariate to open the Bivariate Correlation dialog box, as you can see. In this dialog box, move all your independent variables from the box on the left to the variables box on the right. In my case, I will move gender, age of patients, and blood pressure of patients, which are my independent variables, to the variables box on the right. Remember that the log of age and the log of blood pressure are not part of my original data set. Now, come down to the correlation coefficient section. As you can see here, the Pearson's correlations coefficient box is already checked by default, and the Pearson's correlation will take care of the parametric condition of the variables for correlation analysis. But if you are not sure of your data set passing the parametric conditions for correlation analysis, you are hereby strongly advised to use Spearman's correlation coefficient instead. So, for the purpose of this demonstration, I will include the Spearman's correlation coefficient and check the box for Spearman. This choice will take care of the non-parametric condition of your variables for correlation analysis. Leave the default choice for test of significance as two-tailed, since correlation analysis has to do with the magnitude and direction of a relationship. The box for flag significant correlation is also already checked by default. This information is important so that if there is any significant relationship between two variables in the dataset, it will be indicated with asterisks below the table. Now click OK to produce the parametric and non-parametric correlation test results in the output window. As you can see, the results have been produced. The first table is the Pearson's correlation coefficient table, which provides the output for when the parametric conditions for correlation analysis are met, while the second table is the Spearman's correlation coefficient table, which provides the output for when the parametric conditions for correlation analysis are not met. As you can see, for each table, equal numbers of sample sizes are used in the correlation. That means there was no missing value. By virtue of the p-value designated as Xij, the p-value in each table is less than 0.05, which indicates that there is a significant relationship between pair of variables in the dataset. Now, the question will be, are these relationships highly correlated? This is how you can make your statistical decision. If the correlation coefficient between two variables is equal to or greater than 0.70, then we can say there is a multicollinearity in your dataset or that the variables are highly correlated. But as you can see from the two tables, all the correlation coefficients are less than 0.70. So there is no issue of multicollinearity in the dataset. So the assumption number 5 is not violated. Now let's proceed to test the dataset for significant outliers. Assumption number 6. The assumption number 6 states that there should be no significant outliers in your dataset. In 3 of my previous videos, I have demonstrated how to test for outliers in a dataset using 1. Tookey-Hinges approach, 2. Stem and leaf and box plot approach, and 3. Scatterplot approach. Again, for your interest, I would like to refer you to see those videos on how to identify outliers in a dataset. The link to the videos are given in the description section of this video. But in the interest of this video, I will only demonstrate how to use box plot to identify outliers in a dataset, while I expect you to check out the other methods in my previous videos. Now, go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Descriptive Statistics, and from the drop-down options, click on Explore to open the Explore dialog box. In this dialog box, I will move the age of patients and the blood pressure of patients, which are my continuous variables, to the dependent list box on the upper right. Now, move gender to the factor list box since it is a nominal variable. But since gender is not more than 2 nominal cases, such as male and female, there will be no need to include gender in the test. But if you have a nominal independent variable that has more than 2 cases of factors, you will be expected to move it to the factor list box. So in this case, I will remove gender from the test. Now, click on Statistics to open the Explore Statistics dialog box. In this dialog box, uncheck the box for descriptives. Then check the box for outliers. This selection will produce the box plots of the 2 continuous independent variables that we have entered. Click Continue to close this dialog box. Click on Plots to open the Explore Plots dialog box. In this dialog box, uncheck the box for stem and leaf, and under the box plot section, I will leave the default selection for factor levels together unchanged because I want the SPSS system to produce the box plot as individual figure since no factor variable is included in this test. But if you want the box plot to be plotted together in one figure, then check the radio button for dependent together. That choice is yours. Now click Continue to close this dialog box. In case there are missing values in your dataset, click the button for Options to open the Explore Options dialog box. In this dialog box, select the radio button as appropriate to the way you wish to fix the missing values. However, the default selection of Exclude Case Listwise is the most appropriate option if you have missing values in your dataset. But since my data for this demonstration doesn't have any missing value, I will leave everything here unchanged, and then I will click Continue to close this dialog box. In the Display section, select the radio button for Plots since the only thing we needed are the box plots. Now click OK to process the imputed configurations and produce the results in the output window. As you can see, the box plot for the age of patients and the box plot for the blood pressure of the patients have been produced. But basically, a box plot consists of whiskers above and below the box. These whiskers mark the extremes for maximal and minimal data observed points in the dataset. So any data value outside the whiskers is referred to as outliers, designated by cycles or asterisks. A cycle means low outliers, while asterisk means extreme outliers. So if there are no cycles or asterisks beyond the whiskers, this is an indication that no outliers are present in the dataset. So as you can see in this box plot for age of patients and the blood pressure of patients, there are no cycles or asterisks outside the whiskers, and this indicates that there are no outliers in this dataset. So the assumption number 6 is not violated. As you can see, we have tested the data for all 6 assumptions for binary logistic regression analysis, and we saw that the data has satisfied the parametric conditions and therefore is found tenable for the analysis. So, if your data satisfied all the parametric assumptions like I have demonstrated with my dataset, you can at this point proceed to perform binary logistic regression analysis with your set of data. This is how to perform test of assumptions for binary logistic regression analysis in SPSS, and I hope you'll be able to replicate the procedure to test your own dataset for the assumptions. But right now, we have come to the end of this video. If you like this video and you want to see more video content like this, please like this video by giving it a thumbs up, share this video, and subscribe to my YouTube channel to receive notification every time I publish new and useful content. Subscription is free. Thanks for your time and subscription. Thanks for liking this video, and I hope to see you again in my next video. Bye.